All right, good afternoon again. The next topic we want to talk about is the NVMe hard drives and the evolution of magnetic storage. So my name is Jason Adrian. I'm the Senior Director of the Azure Platform Architecture team at Microsoft.
I'm Mohammed El-Batal. I'm a technologist at the Seagate CTO office.
All right, let's talk about shaping the roadmap of the future of hard drives. We've been talking about this now for many years. I've had conversations 5-6 years ago, and people thought this was a bit crazy. We had some of these same conversations within the OCP work groups back in 2018, 2019, when we had some of the in-person summits. We started making progress. We talked about what are the challenges we're trying to accomplish, what do we actually need to get done, and why does putting a drive on NVMe make sense? And I think over the past couple of years, we're starting to see the clarity, and everyone's starting to understand that this is actually going to add value, to your product and to your business. So we've officially established the OCP workstream. Instead of just having ad hoc conversations, we set up the workstream at the end of last year. We've been meeting every other week for quite a while now, going through a lot of the challenges, a lot of the details. We're going to talk about some more of that in just a bit. We made fantastic progress. We had a TPAR 4088 that went into the NVMe specification. That went in a while back, and now with the NVMe 2.0 that many have seen, it's officially in there. So we've got a lot of the basics that we need into the specifications. So over this last year, we've actually had great conversations from a device level, from a system level. We've seen participation from the end customers, such as Microsoft, people who are interested in it, the technology providers of the drives themselves, the interconnect solutions, think about PCI Express switches, the connectors, everything to make this ecosystem healthy and able to make an actual product, and not just a product from a device, but a product from a system perspective. There we go. So let's talk about system architectures in general. If we rewind the clock and we talk about enterprise storage solutions, you might see SAS all over the place. We have multiple chassis. They're daisy chain. You can see, from 12 drives, 50 drives, hundreds of hard drives, right? But in the hyperscale, in the scale-out space, that's not as prevalent anymore. We start building systems that have a CPU with a small number of drives. So if you look on the left-hand side of the image up here, you might see one of two different implementations in the hyperscale space. The one on the left is more of an enterprise SAS architecture where you have a SAS IOC, and if you have a large number of devices, you might have some SAS expanders. Instead of tens of drives, maybe you're getting close to 100 drives. The solution that's shown on the right-hand side of that left part is if you're using SATA, you might go down a few different paths. If you need a small number of drives, you can directly connect it to the host CPU. If you need a large amount, maybe you're putting a SAS IOC and running STP to get those drives connected, or you may also have to put a SAS expander to make it look more like the left solution. But it's a hybrid of what you're seeing out there. And if we talk about where we actually want to go, we want to go to what's shown on the right. Let's get out some of that superfluous silicon that we don't necessarily need. We don't need a cable outside of the system. We don't need all the capabilities that SAS and SCSI have been providing all these years. So now we want to directly connect it to the CPU if it's a small distribution of drives. And again, if it's large, we still need a fan-out solution. So PCI Express switches, they're here today. We use them in many of our products. And we'll talk about how that's also going to enable the NVMe hard drive ecosystem as we build some of these very large systems. So again, why do we care about this? I mentioned that maybe SAS and SATA have some capabilities we care about, but we don't use a lot of it. We're not daisy chaining out. So being able to remove that, so proprietary drivers and complicated stacks, and go to a much more simplified NVMe stack adds a lot of value. And guess what? We're already doing that for SSDs. Let's have some consistency across the board. Let's get rid of some of this uniqueness. The other thing that we want to do is have support from multiple actuators. I know we're at this precipice of, do we stay single? Do we go to dual actuator? Well, with SAS, there's actually a very clear path. With SATA, it's a little bit more complicated. When we talk about NVMe hard drives, we thought about that from day one, and we made sure that's going to scale. So it may not be a dual actuator that you see today. Maybe in the future it's quad actuator. Maybe these devices go out of form factor. Maybe we have even more over the course of time. Let's set us up right now so when we're there in the future, we're ready to go. And I think that's kind of the message I delivered a few years ago when we had some of these brainstorming conversations about why we would do this. There's a lot of skepticism of, we don't need it today. The problem is technology takes time to develop. It's not going to present itself overnight. So what we've done is kind of set the groundwork for the success of the future. In just a few minutes, you're going to see how far we've actually come. And one last bit to touch upon from a use case perspective. Today, I mentioned NVMe over Fabrics. I talk about computational storage. What if you don't want to have a host CPU in the way of your data? If you have SAS or SATA, most likely you're going through the host complex. You get that system onto the PCI Express bus. Now you have the ability to use accelerators. Maybe your system topologies, maybe what you think is possible from the silicon that you're using today might change in the future. A lot of people think about this when they talk about SSDs, but the world's data is actually stored on hard drives. The vast majority of it, almost everything you interact with in your life is on a hard drive. So we've got to make sure that those capabilities scale. So what have we done in the work group? I want to talk about what's done and kind of what's ongoing as we move towards the specification contribution. So we've aligned on the form factor. We're going to start with a traditional 3.5-inch, 1-inch thick hard drive that everybody knows and loves today. So it looks the same. We've also agreed on the power requirements. We actually leveraged some of the specifications from the past, and we're continuing it forward, and we made some tweaks on the 12 and 5 volts. We had some agreement within the work group, so we think we're set up for success there. We're going to talk about single versus dual port. We've aligned that single port is probably going to be the highest volume, so a single lane of PCIe, maybe it's Gen 3, maybe it's Gen 4, is going to be what we target. But if we want to replace SAS and SATA, we need a dual port capability. So that's why we have dual porting here, so you could have multiple hosts connecting to a device, just like you do in a SAS infrastructure today. We talked about the connectors. We'll go through a little bit more of that in a few slides. Basically sticking with traditional SAS SATA connectors. Maybe we'll have some tweaks to the connectors themselves over time, but right now we have pretty good line of sight for PCI Express Gen 3 with existing connectors. I talked about link speed. So we want to support Gen 4 in the specification, but most devices may only need Gen 3. So a device can support a substantially lower performance than it might need in the future. But we want to make sure that we're forward-looking. So if we're talking dual quad actuators in the future, you're going to start to overrun on Gen 3. So in our specification, we're going all the way up to Gen 4 for nice-to-haves. And we're going to do SRIS support. This is one of the things that when we talk about PCI Express and sending over clock, that makes things complicated. And if you're building a SAS box today, you're not doing it. You have an embedded clock. So we're going to go down that path from day one. We will make it successful. That said, we have a few opens. We're talking about some of the feature requirements, what might be unique in an NVMe hard drive versus a SAS and SATA. How do we bring some of the things that we're used to in those infrastructures into the NVMe workstreams? And then security. Everybody's interested in security. SAS and SATA hadn't really thought too much about that. You'll see different things, whether it's firmware attestation, making sure your device is what you think it is. We're actually making sure we set that groundwork now for a successful rollout when these devices become available. So how do we gauge success? Everything is about cost of ownership. If we come in and we say that the TCO is more expensive for an NVMe hard drive, if you add substantial value, it's going to make sense. But if you just have this as a replacement for SAS and SATA, we actually have two things we really need to think about. One is the cost of the system itself. What are we putting in there, whether it's SAS versus PCI Express switches? So that needs to be at parity or better, and we have line of sight to doing that. Then we talk about power. This one's often overlooked when we think about a TCO. TCO is often CapEx focused. But if you can pull out a little bit of power on the device side, or a little bit of power by getting rid of two, like a SAS IOC and a SAS expander, replace it with a single switch, or if you're directly connecting it to a CPU, you're pulling out a few watts. A few watts doesn't sound like a lot, but when you're deploying millions of spindles a year, that adds up. And you saw in some conversations earlier today, we're trying to go carbon neutral, water positive. All of this fits into that mantra. So multiple vendor support. This goes across the board, not just from a device perspective. This is the PCI Express switches and the connectors. So we've got a line of sight for that across the board. So we will never be single source. That's always critical when we do something at scale. And then technology readiness. And this is actually what the next couple of slides are going to be about. We have a lot of the interconnects, both from the switches and the connectors. The one missing piece has been the NVMe hard drive. So Mohammed, you want to?
Absolutely. Thank you, Jason. Yeah, that's a great summary. What I'd like to go through is actually show you the drive. It's born, right? So this is the first generation of engineering drives, right? They're pre-EDUs, pre-engineering demo drives. So but keep in mind that what Jason was talking about was what we're hoping to achieve in reality. Seagate has put enough resources to make this happen from scratch, actually, and we've been very much dedicated to provide a solution that is flexible, that is not going to be a new drive. It's the nearline drive you're used to. It's the same SKU that we're going to be shipping in the future. We're enabling our future drive with tri-mode SerDes and with 3 IP blocks that are for the interface. So you got an NVMe IP block that can be enabled through firmware, a SAS IP block or SATA IP block within our SoC. And that basically is leveraged from SSD NVMe generational IP that we've created. What does that mean? So for us, it's the EDU availability in September 22. That's going to be for key customers. And we're happy to engage with more customers as we go to customer development units in 2024. The idea is we don't want to rush things. We want to make sure that the generational shifts like this in a data center, do it at a natural transition point when we're ready to upgrade systems, racks, and enable something that is evolving into the next generation fabric enablement of nearline storage. So mass storage has been a DAS storage, direct attached storage, for a long time. It's time for it to evolve and move into a fabric attached. So, coming up to plugging into existing OCP storage, with the slot being compatible, the SATA connector still fits, right? It's just a matter of changing some of the electronics in that chassis, whether it's a Bryce Canyon or future versions of that. You can actually just change the electronics, and now you have a system that's capable, of interacting with a Gen 3 type solution. If it was designed for SAS 3, typically the SerDes are able to get connectivity and work. Could require some tweaks, but that's the target is we got as close as we can. Let me see here. It's not working anymore. Clicker. So how did we get there? The initial drive that I showed you here, we started with all the signals that are on a U.2 SSD. So we took a U.2 SFF 8639 connector, and we put every signal that you have on an SSD today with regards to ref clocks, and we put we connected dual port, we connected everything that we needed to validate back in a mount, right? So we're going to go in with this drive in testing for system level testing, and we're going to try to connect it into systems that are already for, equipped with capability to run clocked PCI, and then back that out to SRIS with spectrum clocking, and try to work through the PERST signal as the reset signal. That we spent a lot of time talking about that in the committee or in the conversation within the working group. The idea is we want to take our time and validate all these reductions in signals to bring PCIe to become more of an interface replacement to SAS and SATA. Otherwise, we're going to continue to consider it a bus interface, which is not what we want. We want to make it simplified and connect into where SAS and SATA used to connect. So again, the SKU proliferation was a concern within every commodity manufacturer, they hate, amplifying the SKUs that they have. So we kind of came to the conclusion as a team that basically having the same physical hardware that is capable with different firmware loads down the stream in the manufacturing line can make it into an NVMe drive, SATA drive, or SAS drive, helps the transition becoming a little easier for the end user, right? So eventually, the vision is that we would potentially put NVMe firmware on all the drives we're shipping if, down the road, if that's the only thing that we can make up for the gap that's needed by SAS and SATA. Today, we have a lot of stable drivers, right? Whether it's SATA drivers, people are attached to it saying, hey, it's stable, it's working. Yes, SAS, it's been a long time since we had to think about replacing SAS. But, with time, the NVMe driver is, non-proprietary. It's ubiquitous. It sits in your OS, and it basically tested by millions and billions of deployments. So, I think what we're hoping for is we get more stability out of an NVMe driver than we've ever had with SAS and SATA drivers. But it will take time, so we're ready for that transition. We'll do it at the pace of what the industry can take. But we will have two SKUs, one for single port, optimizing with a SATA connector, and one for dual port, optimized with a SAS connector. So for enterprise, they can still ship the dual port SAS like dual port NVMe. It will have all the hot plug requirements and reservations and HA capability. For the cloud, for single port, it'll become, similar to what we're having and used to. So please go ahead.
All right, so let's talk about how you actually optimize TCO. The best way to do that in a hard drive-based solution is to connect your drives directly to your CPU. And that doesn't happen a lot, right? So if you have a 12-drive solution, maybe you do. But if you have 30, 40, 100 drives, that sometimes may not be practical, but they'll have an ask on that in a bit. In the meantime, we have PCI Express switches from multiple vendors. We have tri-mode IOCs that allow you to connect a decent amount of drives if you can avoid going to a very large PCI Express switch. So there are options out there today. We don't need new technology to make this work, but we might need some tweaks to make it even better in the future. And that's actually what the ask is about now. So let's talk about the future. Where do we want to go as an industry? Where do we want to go with OCP as well? So I mentioned, let's connect it directly to the host complex. But what is a host complex? Is that a generic CPU, like an x86 or an ARM? Or is this something like a DPU? You see a lot of news out there talking about how we harden pipelines away from general purpose cores. And this is where the gears start to click about why we're talking about NVMe hard drives. If you're going to go build an ASIC, or you're going to go build an accelerator for a part of a CPU, you probably don't have a SAS controller. There are very few of those out there. You're going to have SATA, but you're not going to get all the benefits of SAS. NVMe hard drive is going to bring a lot of the benefits that we liked from SAS into the NVMe space. So this is going to actually be very exciting. And for the connectivity vendors, we actually do have a request on PCI Express switches. Today's switches aren't meant for this type of fairly low workload. They're meant for very high lane count, very high speed devices. So you look at a Gen 4 or Gen 5 PCI Express switches, these are terabits of data rates. Hard drives don't move that fast. So what we actually want, if you're thinking from an upstream perspective to enable a lot of drives, give us a by 8 or by 16 host connect. So maybe that's a by 16 Gen 4 or by 8 Gen 5. That's great. We're getting data in and out of the switch. And all the downstream lanes, hard drives don't need a PCI Express Gen 5 PHY. They're not moving that fast. In fact, today a Gen 3 is going to take us quite a while for both single and dual actuator. But to make sure we're really forward-looking, as Mohammed mentioned, it's going to take a few years before these products are ready to ship. By that time, having Gen 4 capabilities in the switch is going to be critical. So while we may have dual actuator then and can probably survive in a single Gen 3 PHY, Let's get those Gen 4 PHYs out because these products last quite a long time. We don't want to build a new storage solution in a few years from now as these data rates go up. So let's work on getting ideal switching silicon. So the call to action, we've mentioned that we've seen the physical device here, but you can actually see a live demo. If you go see the storage experience booth, it's in the back right-hand side of the expo hall. These are real, they're running. You can see the traffic that's out there. The other questions we want to make sure we're bringing into this work stream of how do we engage further, not just from a device, but from a systems perspective. What else do we need in this ecosystem? How do we move forward? Let's contribute reference designs. Let's figure out how we move the needle forward. And from our part, we'll be contributing the specification by the end of this year. And depending on holidays, it may slip into the beginning of next year. But nothing is going to be new in the spec that if you have been participating in the workstream you haven't seen. So we've been very open, very collaborative. We really are looking for that engagement. Like, what are we missing? Is there anything else we should be considering right now? Because once you set a spec and we start driving it through standards bodies, it's a lot harder to think about new ideas or new requirements that go into that. So if you haven't already, check it out. Look what we've done over the last year. We have a mailing list for the NVMe hard drive work group. We have meetings every other week. Join us. And this is definitely a journey together. So we're looking forward to more of that.
Absolutely. I think Jason said is I would reinforce the fact that we're here to innovate and create open hardware architectures. And so there's an opportunity here. With HDDs come a modest level of performance requirement at the chip level. So the chip that's orchestrating and connecting to all these drives, if somebody was telling you put 100 SSDs and put them on one chip and put added value and create additional manipulation of the data on the way, or put Ethernet connections. You need a lot more when you have SSDs. But if you have HDDs and you're trying to do it at a cost point of what an FBOD, a fabric attached JBOD, you don't need a lot more than just connectivity with basic processing capability to handle the IOPS of 100 drives or the bandwidth of 100 drives. So it opens the doorway for us to innovate around silicon, future silicon. So we welcome additional silicon investments in SoCs and other things around this concept to further enable the ecosystem. I think it helps us greatly to envision that happening. And NVMe with drives that are capable of features like CMB, controller memory buffer, where streamlining the NVMe or fabric capability becomes a possibility without having to burden an x86 or a CPU, a head node, with all the work that's needed to do the translation of protocol and then fabric enablement. So with that, I would just like to, thank you, Jason.
Thank you for helping, and we have a first device. So we have a few minutes now. We can answer some questions. We'll also have a video recording from the demo. So that'll be next, so we can entertain a few questions now, and if we don't get them all in, we can certainly talk again after the video. So with that, open it up for questions.
Okay. Jason, we do have one online question.
Oh, maybe we'll address the online question first.
Yeah, will the NVMe HDD support SM bus or I3C basic? The OCP security ask. A sharing of 32 devices on a single bus is problematic.
Great question. This is actually one of the conversations we had in the workstream. Should we have out-of-band management? As a group, we decided no, that we're not going to support the out-of-band management, but we will support in-band management. Hopefully that answers the question. So definitely a topic of debate for quite a while. I think we had a lot of conversations on that. I think people's minds, including my own, changed over time.
Yeah, first of all, I want to congratulate for the first ever NVMe HDD access to see the demo. A quick question, I saw your EDU is a PCIe Gen 4 with 2022. I assume this also point to the CDU will be a Gen 4 as well. Is that my understanding correct in this case?
Sorry, I didn't hear the last part.
The Gen 4, I saw your slide saying that the EDU 2022 is a Gen 4, right? Gen 4 based on the device.
Correct, yeah.
So this means that your CDU is also be Gen 4?
Yes.
Okay.
I think the plan is to, today our IP blocks are all Gen 4 capable, and we're going to have IP blocks that are Gen 5. But if there's benefit from using faster IP blocks just for silicon integration and reuse of IP blocks within SoC architectures, we'll do that. But we're starting at right now the IP blocks that we have are Gen 4, so we're going to use those. We're not going to take a step back to Gen 3 and limit ourselves to Gen 3. But you can use the expectation. I think Amphenol showed some simulations for the SATA connector that it can actually run Gen 3 up to Gen 3 PCIe signal integrity wise through the basic connector and PCB that FR408 or whatever that we're using in our current systems. For the SAS connector, they showed that if you use a 24 gigabit SAS version of the connector, you can actually run Gen 4 PCIe comfortably with the same margins that we saw on Gen 3 with SATA connector. So right now we're recommending if you're for the first generation drives, more likely we're going to run Gen 3 with the SATA, and Gen 4 you can run Gen 4 with the SAS SKU.
Okay. So can I assume that the driver is because of the performance, or did you see any silicon?
Again, NVMe drives were never about performance, right? It was just not about the performance aspect of it. It was about the connectivity and the overall enabling the features and the capability of the protocol. But if you can find a way to benefit from the performance, might as well from a bandwidth perspective. In the future, as we go to multi-actuator, dual actuator, quad actuator, potentially you'll start being able to leverage a lot of that performance into PCI.
Okay, got it. Thank you.
And maybe I'll add a little bit more. So when we think about TCO, asking about Gen 3 versus Gen 4, in the spec we're saying it must support a minimum of Gen 3 and it could support greater. And then if you think about when we're building systems based on this, we'll look at the power end to end, both from the CPU or the switch silicon or the device, and we'll choose to run it at Gen 4 or Gen 3 to save the most power. I mean, that's kind of the theme of what we're trying to do here, reduce power. There's no reason to put even an extra half a watt if you don't need the performance. So Gen 3 should be more than enough for our throughput, so even if a PHY or even both ends of the link supported Gen 4, we may not run it at a Gen 4.
Absolutely.
Any other questions?